of Code Jam. We hope that these sessions are being helpful for you people. I am Arvarsha Bhantia, a member of Google Developer Student Club at RVCE. And today we will be looking into some important sorting and searching algorithms. First, we'll be seeing the working of those algorithms along with their codes. And at the end, we'll be solving some application-based problems using these algorithms that we learned. So we are aiming it to be a session of 1.5 hours. First 50 minutes we will spend uh, learning the working of those algorithms. The session is very short, so I'll just give an intuition of all the algorithms so that in the future, whenever you're learning on your own, it won't be difficult for you. Then the next 30 minutes we will solve coding questions, and last 10 minutes we will try to keep it for any discussion or question and answers. So let's get started. There are many searching algorithms. Here we will be discussing few important ones, that is linear search, binary search and interpolation search. Again, in these three, binary search is the most important one. First we will see how linear search is working. Before starting, what is search? Searching is finding an element in any given data structure. That would be array tree, any data structure, finding the target element. The target element is most commonly called as key element. So the first search and the most simpler, this is like very easy peasy search, linear search. Now if I give you a deck of cards, normal playing cards, I ask you to search for a card, what will you do? You will go one by one. You will search from the beginning. Is this the card? No. You will keep it aside. Then the next card. Is that the card? No. You will keep it aside. So like that, you will search the entire deck of the card in a sequential manner. That is what it says. Just presented. One second. Yeah, so in linear search, you will search the elements in a sequential manner as you search the card in a deck. Now, what will be your algorithm while searching that card? From the beginning, you will start and you will search until two conditions, until you find the target card that I asked you to find, or you will reach the end of the deck without finding that card. These are the two conditions when you will stop searching. Uh, that is what I have written here. Till the desired element is found, you'll search, or till the end of the list is encountered. And this sequential manner searching, in this, it need not, your deck of cards, that is your list, need not be sorted. Of course, if it's sorted, it will be more easier for you to find that card. You'll already have an intuition in your mind where that card is present. But even if it's unsorted, you will go one by one and you'll search it. The linear search, it works even if the your array is unsorted. But if I give you thousands of cards with different numbers, it will be very time consuming for you to do that one by one. So this linear search is time consuming and inefficient for big lists. We'll see this example here. It is an array of size 6. I tell you to find 12 in this array. You will start from the first number. Is at 0 index, it is 8. Is 8 the element that I told you to find? No. Then go to the next element. That is 7. Is 7 the element that I asked you to find? No. You will go to the next element. Is 15 the element? No. Is 12 the element? Yes. So you have found the target element, you will return it. Since it is a sequential search, its time complexity is big of n. No, if in the same example, if I ask you to find the element 9, you will start from the beginning, come till the end. That is, will cover all the elements. Not only that, if I ask you to find an element which is not at all present in the array, if I ask you to find 10, it is not there in the array, right? So from the beginning, you will start. You will traverse the entire array. That you will reach till the end, but still you haven't found 10. That is, you will cover all the elements. So its time complexity will be big O of n. This is the code, quite simple. I'm sure you guys know, but I'll just tell you once. This is the function. Search is a function. Int is the data type that will be returning. That is the index of the target element. Array, it is the list of elements. N is the size and X is the key element. You will use only one for loop for int I is equal to 0 till n. That is big of n, right? You'll traverse the entire array. If the element that you're standing on is equal to the target element, you'll return that index, or else you'll return -1. So this was easy. Now coming to binary search. What happened in sequential search, as I told you, from beginning you traverse till the end, it takes big of your time complexity. And I also mentioned that if the array is sorted, it would be easier for you. So that is what we'll do in binary search. In binary search, we will sort the array, and this will work only if the array is sorted. In this binary search, you need to remember only one formula. That is mid is equal to highest index plus lowest index divided by 2. That is, we'll find the middle of the array. This binary search, it is based on decrease and conquer technique. Some say it is divide and conquer, but it is not, because in divide and conquer you divide the problem into two subproblems. You solve both the subproblems and then you merge it to find the answer. But in binary search, we concentrate on only one subproblem. We divide it for sure, divide, but we won't solve both the subproblems. We will solve only one subproblems. So it is decrease and conquer. These conditions you'll understand if I explain the example. Just see this example. This is the given array of size 10. What is the lowest index? The first one, L is equal to 0. Highest one is H is equal to 9. What will be the middle one? 0 plus 9 divided by 2 is 4.5, that is 4. Now, the tag, this is sorted. If the array is not sorted, you have to sort it. I have already, this is already unsorted array. The target element I told you to find is search 23. Search 23. Now is 23, is this equal to 23? Mid element 16? No, it is not. Is the search element greater or lesser than the key element? It is greater, of course. It is 23 is greater than 16. So I'll discard the left subarray and I'll concentrate only on the right subarray. I'll increase left by 1. Now my left is equal to 5. I again find the mid of only this portion. That is 5 plus 9 divided by 2. I get 7. At 7 I have 56, which is again not equal to the key element. And 23 is lesser than 56. So I'll discard the right part. I'll only concentrate on these two people, 23 and 38. This is lowest index, this is highest index. Low plus high divided by 2, you will get 5. Mid is 5. Is 5 your target element? Yes. You will return that element. And this time complexity is big of log of n, which is much better than your linear search. Now in interpolation search, again in binary search, why to find one is the mid element if we have better estimates of finding the key element in the array. In this example, if I ask you to find some element which is present nearby the mid, that's nice. But if I tell you to find something which is like little far from the mid, then the exact mid of the array might not be a good option. There are better options, and this interpolation search comes to the rescue there. Instead of finding the exact mid element, it follows a different formula. That is lower index plus highest minus lower index divided by the elements at the highest index minus the element at the lowest index. X is the key element which I ask you to find, minus array of the element that is present at lower index. This formula you need to remember. There was a condition for binary search that the array should be sorted. In interpolation search, there is an additional condition that the array should be uniformly distributed. It should be sorted. Additional condition, it should be uniformly distributed. For example, 1, 2, 3, 4, 5, the difference is 1, or 2, 4, 6, 8, the difference is 2. The difference between the numbers should be equal. We will see an example. See, in this example, if I would use binary search, I would get my mid to be 5, and my key element that I'll tell you is 3. Key element is 3, but you'll find the mid to be 5 using binary search. Now, if I use interpolation search using the formula, I'll get my mid directly to be equal to 2. That is index 2. Index 2 will be 0, 1, and 2. Yes, at index 2, I've directly got the mid element. So this is usually faster than binary search. Note that usually, not always. So its average time complexity is better than your binary search. It is log of n. In binary, it was log of n. But remember, worst case can lead you to the time complexity of linear search. That is big O of n. So depending on the applications, you have to use the algorithm. we saw the working of linear search. We'll just see how binary search works quickly. It's very easy. Now see here. Given an array, it is an Leetcode question. Given an array of integers nums, which is sorted, it is already sorted. Remember, if it's not sorted, you have to sort it first. Which is sorted in ascending order. It is already given in ascending order. And an integer target. Write a function to search target in nums. If it exists, return index. If it doesn't exist, return 1 minus 1. They have given a condition here that it should be big of n, sorry, log of n only. If they would be fine with big of n, we would do linear search, which is more easier. The code is more easier. But they have clearly mentioned it should be in log of n time complexity. And we know who has log of n. It is binary search. So this is the code of the binary search. As explained, you will have a left index, which will be the starting index 0. You will have a right index, which will be the last index, that is nums.size minus 1. Or nums.size means n, the size of the array, minus 1. That is the last index. This is the main portion of the binary search, and this is the condition which will lead you to come out of the algorithm. If the left index becomes greater than your right index, that means you have to stop. Now we'll take 0 and 1. In this example, the first index is minus 1, first number is minus 1, last number is 12. My target is 9. I'll find the mid, left plus right divided by 2. I'll get some mid element. We'll take this example itself. I'll get 16 as the mid element. Okay, fine. Now, is my mid equal to target? If it is equal to target, you will return your mid. You're done. But if it's not, case 2, if it's not mid, you will check if your target element is greater or lesser than your mid. If it's your target element is greater than your mid, then you'll discard the left portion and concentrate on your right portion. You will increase the index of the left by 1. If not, you will discard the right portion and concentrate on your left portion. That is, you'll decrease your mid by 1. If you get an answer, you'll return mid here, or else you'll return minus 1 here. Now, this binary search, it can be twisted. This was the straightforward algorithm of binary search. Little bit, very, very little, small, minute twist. Same, given a sorted array of distinct integers and a target value, return the index if the target is found. That is what we did in binary search. If not, return the index where it would be if it were inserted in order. In what we did in the previous problem, if we didn't find the element, we would return minus 1. Here they are asking, if you did find, return the index, no issues. But if you didn't find, return me the index where I would insert that element, which you have not found. And same log of n. We'll see the problem on the Leetcode. We'll have better understanding. See this example test case. 1, 3, 5, 6. Target is 5. I have found 5. I have returned the index where I found 5. This is at second index. In the second example, they are asking me to find 2, which is not at all there in the array. What did it tell? If it's not there in the array, return me the index where I would insert it. If I insert 2, I would insert it between 1 and 3, which should be at index 1. So at index 1, I would insert 2. So that is what I have to return. Now what I have done here, I've just copy pasted the binary search algorithm that we saw in the previous problem. Same, left and right you will declare, and this is the ditto binary search algorithm. In this problem, if I ask you to find 100, which is which is greater than 91, it is sorted, and it is greater than 91, 100. I didn't find 100, right? So I'll insert 100 after 91, that is at 10th index. After the last index, I would insert it. So if target is greater than your nums of right, if it's greater than your last element, you will simply return right plus 1. That will be your first condition. If then you will check for the mid, this. If you're able to find the element, you will return your answer here, return mid. If you didn't find the element, you will return left. Here, if I ask you find 13, you'll check mid is here, again some mid is here, some, just assume that 17. I ask you to find 17, which is between 16 and 23. but my lower value is at 5. Always, if you try run this code, you will see that you will be able to insert that element at the lower index. 17 will come between 16 and 23. To insert 17, I'll have to push 23 to the right. And the 17 will sit at L is equal to 5 position. So if we didn't find, return left. These are the three things. If target is greater, if target is present, if target is not present, return left. Hope you have understood the search algorithms. Done. You're done with searching now. We'll quickly look into now some sorting algorithms. Again, guys, there are many sorting algorithms, but here we will be just telling you about 5 of these, the most important ones that you should know. First one being bubble sort, second one selection sort, third one insertion sort, fourth one merge sort, fifth one quick sort. This bubble and selection sort codes are quite similar. I would tell these two are in one category and these two are in another category. We'll start with bubble sort now. Uh, Now, if I give you two elements, say 5 and 4, and I asked you to sort them in ascending order, what you will do, you will just swap them 4 and 5. I gave you 5, 4. I ask you to sort in ascending order. You will swap 5, 4 and give me back 4, 5. That is what exactly bubble sort does. Repeated swapping for the entire array. I just gave you two elements, but for the entire array, it has to be repeated swapping. So repeatedly swapping the adjacent elements if they are in the wrong order. Only if required, you will swap the elements in your bubble sort. Again, this is not suitable for large data set. You see, any simplest algorithm, any brute force algorithm will not be efficient. You will have to make it efficient using other algorithms. Like on the similar lines, bubble sort is not suitable for larger arrays. Bubble sort algorithm, you'll understand this if you see the example. Okay, we'll see the. We'll just see the slide one by one. This is the array 6035. You start with your first iteration, step 1. Compare your first two elements, 6 and 0. It should have been in the different order because it should have been in ascending. So I swap 06, 06. The next we'll compare 6, 3. It should have been in the other order. I'll swap 3, 6. Again I'll compare 6, 5. No, it should have been in the other order. I'll swap. It will become 5, 6. So this is sorted. So like that, what happens is in ascending order, the largest element, that is 6, gets bubbled up to the end of the array. So now this portion is sorted. Now in the next step, we'll be concentrating only on the unsorted portion. Just ignore the 6. Like you are done with that. Now 035 again 03, compare. It's proper, no need of swapping. 35, it's proper, no need of swapping. You're done. Second step, second iteration done. Third iteration. In second iteration, 5, 6 got sorted. In third iteration, you'll compare only these two, 0 and 3. It is already sorted. No need of any swapping. So you see, for 4 numbers, we did 3 iterations. That is, total number of passes will be n minus 1, and total number of comparison will be given by the formula n into n minus 1 divided by 2. In sorting algorithms, along with the time complexity, there is two important things that you should know for every sorting algorithm, whether it is an in-place sorting algorithm and whether it is a stable sorting algorithm. What do you mean by in-place? In-place means the array that I give you, you're performing your whatever you want to do, you're doing it inside that array. You're not using any extra storage space to sort your array. So it means in place. You're doing it within your array, within whatever I've given you. You're not using any extra memory there. And so is this bubble sort in place? Yes. I'm doing whatever I'm doing it inside itself. So it is an in place. Whether it is a stable sort. What is stable sort? Bubble sort is stable. I'll tell you one second. I'll give you 2, 2, 2, 2. This is my area 2, 2, 2, 2. This 2 is at the first position. Similarly, this 2 is at the second position, this 2 is at the third position, and this 2 is at the fourth position. Now, what stable sort means, after I sort this array, the algorithm won't know if it's already sorted. It will perform its steps. What it is desired to do, it will do. After sorting this, if I get the same order again, if this 2 which is present at the first index, if it's still present in the same way it is, then it is called stable sort. If there's any changes, if this becomes like this 2 came here, this 2 came here, and then rest is same. If after sorting, if this gets exchanged, still it is sorted only 2 2 2 2, it is sorted, but this 2 was this 2 was supposed to come first. If this happens, then it's not stable sort. Bubble sort, it is stable. It will maintain your position of the elements as it is in your original array. Okay, so hope you have understood bubble sort. We will see the code. Once you have understood what do you say, the algorithms, your code isn't difficult. This is a bubble sort code. This is your driver, main program. This is the same array we have given. This is a function to print. This is so small bubble sort algorithm. That's it. We'll be using two loops. This outer loop is for the iterations. That is n-1 iterations we did. That is for the number of iterations. This inner loop is to traverse to the array in each iteration. For now, ignore the swap. I'll tell you later what it is. So I've used two loops. In the first iteration, I'll go to the entire array. If array of j is greater than j plus 1, if this is a descending order, I'll compare two elements. If that's in descending, I will swap them because I told you to make it in ascending order. I'll swap these elements, array of j and j plus 1. That's it. That is what you keep doing. For every repeatedly, you'll keep doing that. That is what your bubble sort is. Now, to make it a little bit more efficient, if I give you an array which is already sorted, the algorithm doesn't know that it is sorted. I give you an array that is already sorted. If you perform bubble sort again and again all the iterations, it is waste of resources. So what you can do while performing your first iteration, side by side, you can check if anything was swapped in the first iteration. If nothing was swapped in the first iteration, it means that the array is already sorted and there's no need to perform further iterations. That is what I'm doing here. I'm declaring a bool called swapped and I'm keeping it as false. Now in the first iteration, if any swap is performed, the swap becomes true. If no swap is performed, it means that array is already sorted. Before going to the next iteration, it will check if swap is false. If swap is false, there is no need to continue the algorithm because the array given is already sorted. You will return from the algorithm. That is what this swap variable does here. Similarly, we'll see selection sort. Okay. Selection sort, in bubble sort, what we did, we compare the adjacent elements. In selection sort, what we will do, instead of doing that, we will just slightly use a different technique. We will repeatedly, of course, we will find this smallest or largest element based on if I ask you to do it in ascending order and descending order. You'll the selection sort, every iteration you'll find an element, say smallest element, and we'll push it to the beginning. You'll find the smallest element, put it to the start. That in every iteration you'll find one element. In selection sort, there will it will maintain two arrays, sorted array and unsorted array, not separate storage page. Inside the original array itself, it will maintain sorted array separately and unsorted array separately. Algorithm will understand if you see the example. We have done all this. Bubble sort understood, I believe. It's easy though. Selection sort. This is the array I have given you. First iteration. Iterate to the entire array. Smallest element 11. 11. It should have come in the beginning. What is it doing at the end? I'll put it in the beginning. Swap these two. 11. Done. So this is the sorted portion. This is the unsorted portion. No, ignore the sorted portion. Concentrate only on the unsorted portion. Here, which is the next smallest element, 12. 12, it should have come in the beginning. That is in the first place of unsorted array. I'll swap it. 12 came here. Similarly, then 22, 25, 64. So within 4 iterations, last iteration, this is like already sorted. We are not performing any iteration or swapping again. So within 4 iterations, we have completed this selection sort. In bubble sort, we used to compare adjacent elements. In selection sort, minimum element of the entire array. Again, number of iterations n minus 1, comparisons n into n minus 1 divided by 2. Bubble sort also had a time complexity of big of n square. I forgot to mention that. We had used 2 loops, right? 2 loops means blindly n square. Here also selection sort will use 2 loops n square. Is it in place? Yes, I'm not using anything extra. Whatever I'm doing it inside the array. Is it stable? No, selection sort is not stable. Uh, I'll see if I can tell you why selection sort is not stable. Okay, I'll take an array 12, 12 and 11. 12, 12 and 11. Perform selection sort. Which is the minimum element? 11 is the minimum element. I'll just number these 12. This is the first 12. This is the second 12, right? No, perform selection sort. Which is the minimum element? 11 is the minimum element. So according to algorithm, I'll swap this 11 with the first element. 11 will come here. This 12 will stay in the same position. And this 12 which is getting swapped will come back. What is this happening? This 12 should have come here. But it is the second 12 is coming first. The first 12 is going second after we sort it. So the selection sort is not a stable sorting algorithm. This is what you mean by stable. We'll quickly see the code. It is just like bubble sort, it will use 2 for loops. This is the main program, print array. This is your selection sort function. You'll use 2 loops, outer loop for iterations, inner loop for iterating through each iteration. In each iteration, you'll find your minimum index. Once you find your minimum index, just check if your minimum index is not the same as your present index. If it's not, then you'll just swap it. Swap your first element, that is array of 5. Swap your first element in each iteration with your minimum index element. So you will do this in each iteration for this entire I loop. That's it. This is a simple selection sort. We are done. We are done with bubble sort, n square, selection sort, n square. Now, insertion sort. Again, we'll come back to our example of those deck of cards. This time I won't ask you to search an element. I'll give a deck of cards. I'll just simply mix everything. I'll shuffle it. I'll tell you sort it, please. What you will do, you will pick one card. You'll keep it aside. You'll take another card. You'll check where to place it, whether before the card that you kept aside or after that card. Like that, we'll take one by one. You'll take each card and you'll sort it. You'll keep the sorted array separately and your unsorted array separately. So this is what exactly insertion sort does. We have just given it a name, insertion sort. So this works similarly to the way you sort your playing cards. This also maintains 2 arrays within itself, sorted array and unsorted array. Values from the unsorted part are picked and placed in the correct position in the sorted part. That is what you do in your deck of playing cards. If see this example, this is your unsorted array. I'm giving you this. You can imagine these are the cards. I ask you to sort these cards in ascending order of the number it has been assigned. You'll assume your first card 4, it is already sorted. We'll keep it aside. We'll check 3. 3 should have come before. It should have come before 4. So you'll just place it before 4. 3, 4. Then these red ones are already sorted. Green is the key element that I'm considering where to place. Next element 2. 2, it should have come before 3. Okay, I'll place it before 3, no issues. 2, 3, 4. Next 10. 10, let's say it is correct. 12, 12 it is correct. 1, 1 should have come in the beginning, first, at the first place. Okay, I'll place it in the first place. I'll push everything back. As you do this repeatedly, your at the end, your array will be sorted. This is again an in-place sort. This is again an stable sort. Uh, insertion sort will have a worst case complexity of n square, but the best case is big of n. If I give an array which is already sorted 1, 2, 3, 4, 5, 6, you'll check it is already sorted. In one go, you'll check it is already sorted. So big of n will be the best case, worst case n square. If we'll see the code, we'll understand. Insertion sort. Again, this is the main program input. We are giving it from your. This is the function to print. This is the word insertion sort, smaller than the bubble and selection sort. Here, one for loop will do your job. You'll traverse in each iteration for I is equal to 1, 2, 3, 4 till the end of the array. See, notice you're starting from I is equal to 1 because you're assuming the first card that you pick is already sorted. You're starting from the next card. From index 1, you're starting, not from index 0. So you're starting from index 1. You will consider that card as your key element. And this J denotes your sorted part, the left part. Left part is sorted, right? So that is what your J denotes, I minus 1. Now, while, this is a bounding condition, while your array of J, that is your left element, if it's greater than your key, it shouldn't be. You'll have to make it like proper. So what we'll do, array of J plus 1, wait, again, I'll take 3, 2, 1 as my array. The element 1 is sorted. I know my key element is element 2. Key element 2. I'm starting from element 2, that is at index 1. Is this lesser than the previous element? Yes. That shouldn't have been. What I'll do, I'll take this 2, I'll say make this array of J plus 1. Let this be 3. I'll have to push this 3 to the right. Okay, I'm pushing that 3 to the right and this 1 will stay 1. That is what they're doing it here. Array of J plus 1. You have to push this 3 to the right so that you can insert 2 here. So array of J plus 1. In plus 1, you will insert the same element that was previously present. You have done that. Then you'll again reduce your J index. That it becomes like J becomes minus 1. Then in array of J plus 1, you'll insert your key element. What was your key element? 2. Like 2 has disappeared from here, no? So this is where 2 comes back. 2. Hope you have understood this. If you again dry run it, you will understand. Just see this. After the session, like dry run it, I can't take more time. It's a very short session. Hope you'll understand. Now we're done with this. Now merge sort and quick sort. They are like very important. All these algorithms, worst case was big O of n square. Previously, what we saw. Merge sort and quick sort, it will have average complexity of n log n, which is better than your previous sorting algorithms. Merge sort, it is based on divide and conquer, as the name suggests. You will divide the problem given into two problems, solve both the subproblems, and return it back. Now, for example, you are giving me an array to sort. It is an unsorted array you have given me to sort. What I'll do, I'll catch my two friends. One friend is sitting at my left, just imagine. One friend is sitting at my right. I divide the array that you gave me into two parts. I give my left array to my left friend, please sort it. I give my right array to my right friend, please sort it. Okay. So that is what repeatedly keeps happening. So my left friend will give me the left sorted array, right friend will give me the right sorted array. I'll merge them. And I'll merge them, I'll get my answer of an sorted array. If you see this example, understand. This is the unsorted array that you're giving me. I will divide it into two. This is my left sorted array. This is my right, I'm sorry, unsorted. Left sub problem, right sub problems. I'm giving it to my two friends. Please sort and give me back. My friends, just like me, they'll divide the problem into two halves. They'll give it to their two friends. Even this person will divide the problem into two halves. Will give it to his two friends. Again, uh, the person again will divide it into two halves. Will give it to his or her friends. Same for each of them. Now this person, they have only one element. They can't divide it further. So what they'll do, okay, no, I can't divide it further. I'll give it back to the person who gave me. I'll tell that it is a single element. It is already sorted. I'll give it back to you. So this is the answer. Blue one is the unsorted. This orange one is orange yellow. It is sorted. So these two friends will give back the problem. Two will come first. Five will come second. Mm, I'll, okay. So these two will give back similarly 4 7. Similarly 1 3, 2 6. These two they'll consider now. How it is actually sorted, I'll maintain two pointers, pointer I, pointer j. While again combining, while merging, this is how you do it in the algorithm. I'll keep two pointers I and j here. I'll check is the element present at I, which is smaller, I, the ith element or the jth. Ith is smaller. So I'll push I here, I'll put I here and I'll increment it. I becomes here. Now I'll again check. Is this element greater or this element? Sorry, which is smaller? Ascending order is what I told, right? So which is smaller? This the jth element is smaller. Okay, I'll put this here. I'll increment j. J will come here. Again, is 5 smaller or 7? 5 is smaller. I'll put 5 here. Out of bound. Done. Left the problem done. Only j is remaining. There's no need to compare with I because I is already done. So directly j will come here. This is how you sort it. Again, this is already sorted. 1 3 is already subproblems are sorted already. You'll give back to the person who gave you to sort in a sorted fashion. They'll take care of it. They'll use two pointers I and j. They'll sort it back. Then me, who first started dividing the problem, both my left and right friends will give me back their work, their part of work, and I'll sort them up. So this is the intuition behind your merge sort. uh, is it is merge sort in place? No, I'm using extra arrays to divide the problem. I'm using extra people. I'm giving the problem to others to sort it. So it is not an in place. I'm using extra resources. I'm using extra storage space. Is it stable? Yes, merge sort is stable, and its time complexity will be n log n. Now we will see quick sort. What was the issue with merge sort? We used extra space. It was not an in place algorithm. That was the issue. So here quicksort will come to the rescue. Merge sort, it used extra space. That is, it was not an in-place sorting algorithm. Now what quicksort does, it won't use that extra space. We'll first see the intuition, and if you understand the intuition, you understand the working of the quicksort algorithm. This is the array. This is the array that I'm giving you. My step one. Hmm. Here you have to pick a pivot element. Pivot means any key element that you want to sort it first. The pivot element can be anything. It can be just 10, 80, 30, 90, 40. It can be anything. Here we will always consider the first element to be the pivot element. Here 10 will so I said the first element here will take it as pivot element. So this 10 will be our pivot element. Now just if we sort this array 8, 10, 80, 30, 90, 40, how it should look like? It should look like this: 10, 30, 40, 80, 90. So keep this in your mind. This is how it looks if it's sorted. Now in the step 2, okay, you told me to pick a pivot. I have picked a pivot. Now what next? after placing 10 in its correct position. After done placing 10 at its correct position, okay. Now step 2 will be smaller on the left. All the elements that is smaller than 10 will push it to the left. All the element that is larger than your 10 will push it to the right. This is your correct position from the of the 10 from this array. Of course, in the algorithm, you can't have a pre-sorted array. For explaining, to just to understand the intuition behind the work quicksort, consider this. Look at this to understand the working. 10. This is the correct sorted place. This is the right position of 10. 10 is already sorted. The blue dash means the element is sorted. I'll divide this into 2 now. Everything which is lesser than 10 goes to the left. There's nothing there. There's nothing. Nothing here. Everything that is greater than 10 will go to the right. 80 is greater, 30 is greater, 90 is greater, 40 is greater. Everything to the right. Again, recursion. Again, I consider my first element to be the pivot element. Here, 80 will be the pivot element. Now what I'll do, I'll have to place 80 in its correct position. Just like this step, place 80 in its correct position. This is the correct position of 80 from here. This is the correct position, right? So I'll place 80 here, and all the smaller elements from 80 will go to the left. 30 and 40 are smaller, that will go to the left. 90 is greater, it will go to the right. So till now, 10 and 80 are in its correct position already. In the sorted array, it is already in the correct position. Only 30, 40, 90 are left to be sorted. I'll divide it again, 30 and 40. I'll consider 30 to be my pivot element. I'll put 30 in its correct position. It is already in its correct position. So 30 is also sorted now. I'll divide it. Everything less than 30 to the left. There's nothing less than 30 here. Everything greater than 30, 40 to the right. Now, if the element is single element means it is already sorted. So 40 is a single element, it is sorted. We'll give back. This is sorted. 90 here. This 90 to the right, it is already sorted, single element. We'll give back. So this way, if you see, 10, then comes 30, then comes 40, then comes 80, and then comes 90. This is how you sort it. And here, I am not using any extra space. I'm just using pointers. I'll use some pointers, IEJ. Sorry. I'll use some pointers to check if it's sorted or not. I mean, to sort, I'll use some pointers. This, what I've explained just now, it is just an intuition. You have to pick a pivot, first step, any pivot, let it be the same in every step. Place the pivot in its correct position using pointers. Using pointers, you'll check which is lesser, which is greater. Place the pivot in its correct position. Everything lesser than pivot will go to the left. Everything greater than pivot will go to the right. And this will happen recursively. This is an intuition behind quick sort. Now it's exactly 50 minutes. 10:30 is what was merge sort and quick sort. I won't show you the code here. I'll put some links in the chat. Please go through those videos. I've used the same example like this. After the session, go through the videos. Since you have an intuition, it won't be difficult for you to understand. Is there a chat box? Yes. This first link is merge sort, second is quick sort, I believe. Go through these videos to understand its working in depth and with the code. Okay, so we are done. We are done with searching. We are done with linear done, binary done, interpolation done. We are done with sorting as well. Intuition has been understood. Bubble is done, selection is done, insertion done, merge and quick sort also done. These three will have n square worst case, these two n log n average case. Now, next what I said we will be doing, we will be solving some coding questions. Okay, we will start from this one. This is okay. Okay, this is a binary search based problem. Very easy. So what the problem says, it is a Leetcode problem. Okay, sorry, coding ninja. Sorry, yeah. You have been given a sorted array. It is already sorted for binary array. That is what you need. Just a minute. So we'll be looking at 1, 2, 3. I guess 3 problems we'll see now. So you have been given a sorted array called ARR consisting of n elements. N is the size of your array. You are also given an integer k. K is your key element. Now what is your task? Your task is to find the first and last occurrence of k in array. Some notes here. If k is not present in the array, then your first and last occurrence will be -1. And your array may contain duplicate elements. It will contain that. That is what the problem is. Mm, okay. Yeah, this one. So in this array, we'll take this as an example. What they have told in the given array and the given key element, you have to return the first and last occurrence of that key. Now where is one present? This is already sorted. They have given it is already sorted array. My first occurrence of the key element is at first index, and my last occurrence is at the second index. 0, 1, 2. It is at the second index. It's an easy problem, very easy. So return 1 and 2. We'll see this sample test cases to understand more clearly. In this case, you see, it is an array of size 4 and my key element is 2. Is my key element present in the array? No. What they have told, if it's not present, return -1. I'll return -1 as the start, -1 as the end. If it's present, he'll return me the start and end index. Okay, now this you have to solve using log of n, around log of n and 10 complexity. For that, we will use binary search. Sorry, yeah, we have to search the element. Right? It's already sorted. You have to search the element using binary search. We'll do this. See here, I have used binary search twice. If 0, 1, 1, 5, I'll take this. 0, 1, 1, 5, no? 0, 1, 1, 5. And they have asked me the key element is 1. This is my first position of the 1. This is my last position of the 1. Now, if I use binary search here, this is my lower index. This is my higher index. What will be my mid element? 0, 1, 2, 2, 3. My 2, this will be my mid. So I have found L, I have found H. Using those two, L plus H divided by 2, I have found my mid. Now in the mid, there might be more ones present in the left. To find the first occurrence, we will search the left part of the array. To find the last occurrence, we will search the right part of the array. That is what exactly we are doing here. To find the first occurrence. Now if, see, this is also named first occurrence. To find the first occurrence, I'll say S is equal to 0, E is equal, S means start, E means end. I've declared start and end. I've found my mid. This is just like binary search algorithm that we just saw a couple of minutes back. If my array of mid is equal to key, here it is equal. 1 was the key element, mid is equal. Okay, it is equal. What next? It is equal. Store the answer for now. Store the answer. Answer is equal to mid. Store it. And decrement your end by mid -1. I'll store this, I'll save it. Because who knows, I might get an element 1 in the left, or I might not get also. So I'll store the position of this one and I'll just check the left part of the array. So that is what I'm doing, and I'm storing it. I'll decrease end by mid -1 and I'll perform this binary search again. If I'll again get a mid element to be 1, I'll again store it as my answer will get renewed. I mean, its index will change if there is one element here also. If there was an one element in my next loop, this will store my answer. So repeatedly, if you keep performing that, at the end your answer will contain the leftmost position of your key element, and you can return your answer here. I'll again come. First, to find the first occurrence, you'll perform binary search. You'll find the mid element. If mid is equal to key, you'll store it, decrease your end minus 1. Again, perform the search algorithm using S is greater than A. Until this condition is true, keep performing your search algorithm. And at the end, your mid will have an answer, which is, your answer, this variable answer, will contain your first occurrence of your mid. Similarly, for last occurrence, what this is your mid. For last occurrence, I have to search the right array. So I'll increase L by mid minus 1. I'll make this to be my L, and I'll only concentrate on this. This is my L, this is my H. L plus H divided by 2, the same as L. This will be my mid. Is my mid same as key element? Yes. I'll store the answer. I'll store it in the answer. The position of this one, I'll store it in the answer. Then I'll again check the right part to find the more rightest occurrence. To the right, I mean. I'm not finding anything. So whatever is in the answer at the end will be returned. So this is what first occurrence, last occurrence. From here, I'll be calling it. I'll declare a pair because they've asked it to return it in a pair, first and last occurrence. My first occurrence will be my first number. Second occurrence, that is this algorithm. This is my first occurrence. This is my second occurrence. So these two functions will return me the first and last index, and at the end I'll return the pair. So this is how finding the first and last position of an element in a sorted array works. This was easy now. We will see something little more tricky, just little bit, not quite hard. This is a problem on Leetcode. What it says, you guys need not do anything side by side. Like just relax and listen to the explanation. An array R is a mountain if the following properties hold. So they're just calling an array to be a mountain if these conditions are true. This is just a note that always the array will have at least 3 elements. That is a good thing. Now, and okay, fine. Okay, see, these are my array. 0, 1, 0 is my array. It is called a mountain if all the left elements present to this I, I'll say this is my I. If all the left elements present to my I are lesser than the element present at 1. All these are lesser. 0 is lesser, and all the elements are at the right is also lesser. Means this is the highest. This is the highest. If I take this one, 0, 2, 1, 0. 2 is the highest. All the elements at the left is lesser than 2, and even at the right it is lesser than 2. We'll go to the problem. So here, this is array of I. All the elements present to the left are lesser than that element, and also note that they are sorted. They are sorted. See, lesser than they are sorted, and all the elements present to the right are also sorted, but in the opposite fashion. This is sorting in ascending, and this has been sorted in descending order. Now what they have asked me is return me the index I such that this is true. So I have to return this element. In the examples that we took, these are the mountains. I have to return the index where 1 is there. I have to return here the index where 2 is present. I have to return the index here where 10 is present. I have to return here the index where 10 is present. So basically, I have to return the index where the highest element is present. Now you could have done this using linear search also. Find the maximum element. That is what they're asking. Find the maximum element. But see, they have given a note here. You must solve this in big O of log of array of length time complexity. Array of length means n. It means big O of log of n. What has big O of log of n? Binary search. So we have, so this is understood that we'll be using binary search now, because binary search is log of n, exactly as what they are demanding. But in binary search, we want the entire array to be sorted. Here, half of things are sorted. The entire array is not sorted together. This half is sorted in ascending. This half is sorted in descending. So we will be just modifying the binary search a little bit. Mm, okay. For better understanding, we'll code this from beginning. Now what? This is my mountain. They have given an array. They have given me some array. It has elements in a mountain fashion. Highest element is present here. So, these are sorted in ascending. These are sorted in descending with respect to the peak element. Now I have to find the peak element using binary search. That is log of n. Okay. On the array, now I will first perform binary search. I'll find the mid element. Let's see, after finding the mid element, we'll think what to do. We'll consider which example. We'll take this example. This one. Now this is the array given. This is my lower index. This is my higher index. And lower plus higher divided by 2, this will be my mid index. I have found my mid index. We'll first do that. Int s is equal to 0 and my end index, it will be equal to array dot size minus 1. That's my start and end, which means left and right. And just like in binary search, how we do, till s is lesser than or equal to end, we will keep finding my mid element. Mid element will be what? S plus e divided by 2. S plus e divided by 2. Okay, I have found my mid element. Next what? Now next I have to check if the element after mid is greater than the mid. See, in this mountain, in this array mountain, this is one part. This is one part. This is one part. This is one part. Correct. Now, if my mid is present at this part, what we'll do, we'll check if the element after mid is greater than the mid. If it is greater, we will shift yes by mid plus 1, just like we do in binary search. If it is greater, if my what it is, ARR, right? ARR of mid plus 1. If this is greater than my array of mid, please increment your value by mid plus 1. Done. So what we did here is, we found the mid element to be at 5. There is an element which is greater than 5. So I'll increment L. I'll increment L to be M plus 1. So this is my new array now. I have to check, I have to again perform binary search on this array, 10 and 0. Now again, if I perform binary search here, this will be my L, this is my H, that is S and E. This will be my mid element. And in the mid element, I found 10. I found 10, but I don't know if it's the greatest element. I'll check the next element. Is the next element greater? No, it is smaller. Yeah, okay. Is the next element then 10, is it greater? No, it is smaller. So 10 here, it is the greatest element. This was if it is present in the left part. Now what if it is present in the right part? That is either here at this point or somewhere here. We'll do these two together, because if we consider these two together, what will happen? Array of mid should be lesser than mid plus 1. this point will never be lesser than the next point, though that's the greatest point. So we'll take these two together. We'll say else. If that is not the case, just like here, when we consider 10 and 0, 0 was not greater than 10. If that is not the case, then I'll decrement h to be in this position, to be where m is. So I'll take the last index and place it to where m is, which means in my end, I will place my mid. Okay, this should be fine. Now, okay, yeah. Why not mid minus 1? In binary search, we did mid minus 1. Why not mid minus 1? What happens here is, okay, we have to take a proper example. Okay, 0, 2, we'll take this 0, 2, 1 and 0. This itself, give me a minute, I'll see if this works for that condition. 2, 5, 10, 0. This is the mid 10. I've found the mid element here. Okay, this one mid. This is my mid here. In this example, this will be L, this will be H, this will be M. Right? Now is the next element. First condition was if the next element, if array of mid plus 1 is greater than array of mid. Is it? No, it's not. So what we will do? We'll say S is equal to mid plus 1. That is, we'll cancel this and this. We'll say S is this. Then I'll again search in this array. Mid will be, take this as L itself. L and H, mid will be L plus S divided by 2. So this will be mid. Now here is again, you'll again check if the next element is greater. No, it's not. So what we'll do, we'll take H. What we did, we'll take the H to be the mid. So we'll cancel this H and we'll put it here. Why not mid minus 1? It wouldn't work properly. If I would take my H to be mid minus 1, it would just go somewhere here out of bound. This mid minus 1 wouldn't work in our case. So we'll just consider it as mid minus 1. Now here I have done a mistake. S being lesser than or equal to E. This is what we used to do in binary search. But what happens if we take S to be lesser than or equal to E? In the same example, I'll clear this later. Okay. This is L, this is H, this is my mid. I'll increment my L, I'll come here, L and H. After that, I'll get this as my mid. If I consider this as the part, L, H, this is my mid. Is the next element 0 greater than 1? No. So my end will be equal to mid. I'll take my H, I'll put it here. Again, is my L lesser than or equal to H? Yes, according to this condition. Is the L lesser than or equal to H? Yes. I'll again check if the next element is greater than your mid. I've been left with only this. I'll check if the next element is greater than mid. But why to do that? Because I've already done it. It will become a repetitive step. So we'll remove this equal sign. We don't need this here. So this should be our algorithm. This is the case if the mid is present in the left part. This is the case if the mid is in the peak or in the right part. At the end, if you see, the answer will always be available at your lower index. If you try run and see, your answer will be available at a lower index. So we'll just return yes and see if this works. Yes is fine, mid is fine, mid have declared. Array of mid, else run. Okay, this is giving me a wrong answer. Oh, I didn't change this. This should be E of mid. I explained why it should be. Yeah. Now it's fine. We'll submit and check. Only if it is in log of n, it will accept, or it will show time limit exceeded. This problem has been accepted. So I'll just repeat this again. We have to find the peak element in the mountain. For that, I have to understand. I have drawn a mountain. I have understood that the element, the mid element. Well, if I use binary search, the mid can be present here, or here, or here. If it's present here, I'll check if the next element is greater than the mid, so that I can move this side towards the peak element. I have to move this side. So I'll increment s to be mid plus 1. If it is present here, maybe if this is the mid, I have to move this side, right? So I will reduce my E to be mid. This was my previous E. I'll reduce it to be E. So if you keep performing that, at the end, at our lower index, we will have the answer. Written yes. So this was the problem using binary search. We will see last one, wherein you have to sort it first. Okay, this is a three-sum problem. There are there are three variations of this. There's two-sum problem, there is three-sum problem, there's four-sum problem, and so on. I'll be explaining you three-sum directly. So what is the problem state? What is the problem state? Given an integer array nums, return all triplets. Return me all those numbers, triplets. Return me all those three numbers such that this should be, and they shouldn't be same. I shouldn't be equal to j, j shouldn't be equal to k. They should be at different indexes. Return me those three numbers which are present at different indexes, and their sum. Their sum, the sum of the elements present at those index should be 0. Now if I take this example, okay, if I take this example, they're asking me to return all those triplets whose sum is equal to 0, and they shouldn't be duplicate. Here, if I check just by intuition, -1 plus 0 plus 1, that is my one triplet, which will give me 0 as the sum. -1 0 1, -1 0 1 is giving me sum as 0. Again, there is another -1. Now you this three triplets, this one triplet, I have used these three numbers. Now same I can do using this one, this -1. Again I'll get another triplet whose sum will be 0. But though these are different, they've asked me that it should be unique, even if they're not mentioned. Yeah, notice that the solution set must not contain duplicate triplets. Is this containing duplicate triplets? Yes, it is containing. So you need not consider the same kind of solution again. This is one solution. Anything different present, -4, what is it, -1 1 2. Okay, if you consider this -1 -1 and 2, -1 -1 -1 2, this -1 this -1 and this 2, if you sum it up, we are getting 0 as the answer. So they're asking us to return such triplets. Now this can be done by using 3 for loops. Each for loop will check for one index. 3 for loops will return your 3 indexes, and you can use a set to check the if it's unique or not. But what will happen if you use 3 for loops? Your time complexity will become big of n cube. That is too huge. The compiler will tell you the time limit exceeded. So to reduce the work, what we will do, we will first sort this array. We'll sort this array and we'll see if we can do something about it. I'll sort this. It becomes -4 comes first if I sort. -1. Again there's a -1. Again there is a 0, then 1, then there is a 2. 1, 2, 3, 4, 5, 6 elements, 6 elements. Now I've sorted this element. Instead of using 3 for loop, I'll have 1 for loop. This is my ith index. I'll consider this to be my ith index. Using for loop, I'll go through this entire array. I will become 0. It will be 0, then 1, then 2, then 3, then 4, then 5. Like this, it will go through the entire array, not till the end. Somewhere it will stop till here. There are boundary conditions, so I will come till here. I will use 2 more pointers. Since it is already sorted, I'll use 2 more pointers, j and k. So I'll use these pointers, j and k. Remember, the array is sorted. First you have to sort the array. Then you check if the elements present at those 3 indexes sum up to 0. -4 plus -1 plus 2. How much it is? -5 plus 2, which is -3. Is -3 lesser than 0 or -3 is greater than 0? -3 is lesser than 0. So it means we have to increase this -3. To increase this -3, we have to make this 0, right? To make it 0, we'll have to increase the sum value. To increase the sum value, what we'll do, we will increment the j. We will increment the j. Now, when we have incremented j, what we are seeing that this value of j is same as the previous value of j. We don't want duplicates here. So I'll say I have already considered that. I don't want to consider the same number again. I'll again increment j. Okay. Now this time we have got something different number. Again, sum these three values. -4 plus 0 plus 2. How much it is? -2. Is -2 lesser than 0 or greater than 0? It is lesser than 0. To make it equal to 0, that is what they're demanding, right? Return those triplets. Return those triplets whose sum is equal to 0. To make it equal to 0, I have to still increase this value. What I'll do, I'll increment j again. Whenever I want to increment the value, I'll increment j because this is sort of an ascending order. If I increment j, I'll get larger and larger values. Now again sum this up. -4 plus 1 plus 2. How much it is? -4 plus 3 minus 1. It is giving me -1. I have to increment this again. J and j. I'm getting j and k to be at the same position, which is clearly not allowed. See, I is not equal to j, I is not equal to k, and j is not equal to k. So this is not allowed. We will stop here. We are done with this. Next, we will increment I. Keeping I at the first index, we didn't get an answer. Okay, so we'll increment I now. We'll keep I at this position. Similar, very similar to the previous one. We will keep j at this position and k at this position. I, j and k. Now again, take the sum of these three. -1 plus -1 plus 2. How much is this giving me? It is giving -1 plus -1 is -2. -2 plus -2, it is giving me 0. Exactly 0. So I can return the at least one triplet I have found, which is -1, -1 and 2. I have found this. What after you have found? You will change position of both j and k because you are done with that. You will increment j and decrement k because you are done with it. Now we'll check for the other elements. No. Again, check -1 plus 0 plus 1. How much it is? -1 plus 0 plus 1. It is again giving me 0. I have got another 0 from -1 and 0 and 1. I got another 0. No, there can be more numbers. I and j. If I again increment j, what will happen? J and k will come at the same position, which is not allowed. So I'll come out of that. Similarly, I'll increment I. I'll keep I at the next position here. I'll increment I. I will come here. This will be my I next. This will be my j. This will be my k. I'll take the sum. If sum is lesser than 0, I'll increment j. Yes, if sum is greater than 0, I'll decrement k so that I get a lesser value. Like this, you'll perform for all the elements. The same thing has been implemented in this code. If you see this carefully, this is the most important step where we are sorting. Sort nums.begin to nums.end. This is a C++ STL. If I'm not wrong, it takes n log n time complexity. So we are first sorting this. After we have sorted, we will this is they have asked to return as all the triplets, right? And it is a 2D vector. So I'll declare a 2D vector called answer, and at the end I'm returning that answer. Return answer. Then with that, a 2D vector, or you can imagine it as a 2D array, and return the answer at the end. Use 4 is equal to I is equal to 1, I lesser than n, I plus plus. That is what we did here. We started from the first index, we kept incremented I. Okay, done. Now, if this I is same as the previous one, while you're incrementing I, if that I is same as the previous one, there is no use and we don't want that. The algorithm says no duplicate triplets. If it is same as previous one, please increment it. We don't want, we have already considered that number. So we have to declare inside I, inside the for loop of I, we have to declare j and k. J will be I plus 1, k will be the last index. J will be I plus 1 and k will be the last index. Now, while j is lesser than k, see, if j becomes equal to or greater than k, it means you have to come out of this loop. Check if the sum, find the sum. If sum is equal to nums of I plus nums of j, nums of k. We have found some value of sum. If that sum is equal to 0, this is the first case, sum lesser than 0. Second case, sum greater than 0. Third case, if sum is equal to 0. If sum is equal to 0, we'll just push back this those three triplets. We'll put it in a temporary array and we'll push back it to the answer. That is, we have found one answer. Now, if that sum value is lesser than 0, it means we have to increment j. If the sum value is lesser than 0, we have to increment j, because as we increment j, we will get our desired bigger and bigger values. So I'll increment j plus plus. And while incrementing j, you have to make sure that that element is not the same as the previous one. If it's same as the previous one, increment it again. And these are the bounding conditions. If sum is greater than 0, if it's greater than 0, we have to make it less. So I'll decrement k. Once you decrement k, you also have to check that the after element, if while you're decrementing k, you have to check that this element and this element is not same. If it is same, decrement it again. K minus 1 will decrement it again. And you'll keep doing that. If this condition fails, it is not lesser than 0, it is not greater than 0, it means that it is equal to 0. This case is when sum is equal to 0. If sum is equal to 0, create a temporary array, store those three numbers who is giving you the sum as 0, and push that numbers in your 2D array, push that numbers in your answer array, 2D array. It's 2D vector, but I'll call it array. Then after you have got the answer, increment your j, decrement your k, and make sure that your j and k does not contain similar values. If it contains similar values, just like the previous case, then again you change those values. You increment j again, you decrement k again. So like this, you'll find all those triplets, and at the end you will return the answer. So this is how 3-sum works. This is how you make it more efficient. If you use 3 loops, it will be big of n cube. Now using This one, how much time composite it would take? I loop, this I loop, this loop would take big of n, this k for every iteration of I would take around again big of n. So around it, this whole thing, it would come around big of n square, I believe. Mm, yes, around big of n square. One second. Yeah, so that's it. We have seen searching algorithms in that linear, binary, and interpolation. Then we have seen sorting algorithms in that bubble sort, selection sort, insertion sort, merge and quick sort. Please watch those links for even better understanding. This quick sort, it is not a stable sort, it is an in-place sort, which is an advantage over merge sort. And its best case is n log n, or average case is n log n. Worst case, it can take n square. We have seen these problems. That's it. Thank you. If there's any doubts, you can let me know.